In the last few lessons, you might have been wondering, what does all this have to do with deep learning? Well, it turns out these same techniques that we were just studying form the core principles for how differential privacy provides guarantees in the context of deep learning. Previously, we defined perfect privacy as something like a query to a database returns the same value even if we remove any person from that database. If we're able to do that, then no person is really contributing information to the final query, and their privacy is protected. We use this intuition in the description of epsilon delta. In the context of deep learning, we have a similar standard which is based on these ideas, which instead of querying a database, we're training a model. Our definition of perfect privacy would then be something like training a model on a dataset should return the same model, even if we remove any person from the training dataset. So we've replaced, quote, querying a database with training a model on a dataset. In essence, the training process is actually a kind of query. But one should notice that this adds 2 points of complexity which the databases didn't have. First, do we always know where people are referenced in a training dataset? In a database, every row corresponded to a person, so it was very easy to calculate the sensitivity because we could just remove individuals. We knew where all of them were. However, in a training dataset, let's say I'm training a sentiment classifier on movie reviews, I have no idea where all the people are referenced inside of that training dataset because it's just a bunch of natural language. So in some cases, this can actually be quite a bit more challenging. Secondly, neural models rarely ever train to the same state or the same location, even when they're trained on the same dataset twice. So if I train the same deep neural network twice, even if I train over the exact same data, the model is not going to train to the same state. There's already an element of randomness in the training process. So how do we actually prove or create training setups where differential privacy is present? The answer to the first question by default seems to be to treat each training example as a single separate person. Strictly speaking, this is often a bit overzealous, as many examples have no relevance to people at all, but others may have multiple partial individuals contained within that training example. Consider an image which has multiple people contained within it. Localizing exactly where people are referenced, thus how much the model would change if those people were removed, could be quite challenging. But obviously there's a technique we're about to talk about that tries to overcome this. The answer to the second question regarding how models rarely ever train to the same location, how do we know what sensitivity truly is, has several interesting proposed solutions as well, which we'll be discussing shortly. But first, let's suppose a new scenario within which we want to train a deep neural network. As mentioned previously, privacy-preserving technology is ultimately about protecting data owners from individuals or parties that they don't trust. And we only want to add as much noise as is necessary to protect these individuals, as adding excess noise needlessly hurts the model accuracy, while failing to add enough noise might expose someone to privacy risk. Thus, when discussing tools for differential privacy, it's very important to discuss it in the context of different parties who either do or do not trust each other, so that we can make sure that we're using an appropriate technique.